In this discussion, we are going to start a new topic, which is derivative. And since we are doing complex analysis, so here derivative means derivative of complex valued functions. Now the word derivative is not something very new for us. So we have seen this word many times in our calculus class, where we have studied derivative of real valued functions. And we also saw that it has some geometrical meaning, it has some physical meanings. It is one of the important concepts in mathematics. So we know that the only constant in this universe is change. And if you want to record that change, then you need the concept of rate of change. In other words, we are going to need the concept of derivative, which is the rate of change. Okay, so given any function, calculating the derivative means we are calculating the rate of change of that function. So for example, if our function is displacement function, then here rate of change means the velocity. And if we take the function to be velocity, then the rate of change of velocity is acceleration. And similarly, we can find many examples around us. And of course, if we go on further in the complex situation where there are many rates of change and there is a relation between those rates of change. In other words, we have equations involving derivatives, so known as differential equations. So differential equations are used in starting from economics, engineering, psychology, and management sciences. So it has many applications. So the starting point is this concept of derivative. So if we want to extend the concept of derivative from real valued functions to the complex valued function, so we adopt kind of very simple strategy. We just take the same definition and then try to answer the following question. So the first question would be, does it really make sense to define the derivative of a complex valued function? And then if we can define it, then what does this derivative represent? So, and then the next question would be, what is the difference between the real valued function case and the complex valued function case? So there are some similarities. So for example, as I told you, the definition is very similar. And then in the complex case, we also have the sum of derivative, the sum formula, the product formula, the quotient formula, and we can also use the same L'Hopital rule. I mean, when I say same, it means very similar to the real case. But then there are some differences as well, and we will see those differences from time to time in our discussion. So for example, one of the differences, the mean value theorem for derivatives does not hold in the complex case, and we will see why it does not hold, and etc. Many other differences are there. Now, starting with a review of the real derivative case, if we have a function of a real valued function of one variable x, then the derivative of the function f at point x0 is defined in the following way. So it is basically the limit of this function, which is f of x minus f of x0 divided by x minus x0, and we take the limit that the point x, the variable x, approaches to point x0. Or we can define in the following way as well. So instead of x approaches to x0, we can just say that delta x approaches to 0, and we have x0 plus delta x minus f of x0 divided by delta x. This is the derivative at point x0. So in other words, if we change the point, then we have some different scenario. In other words, it may happen that the limit for this point x0 exists, and for some other point x1 the limit does not exist. So it really depends at which point we are calculating the derivative. Now let's see what does it represents geometrically. So what are we really calculating here? So if we consider the graph, so this is the function y is equal to f of x, so it has the following graph. Now if we have the point x0 over here and x plus delta x is this point, then this point has the following coordinates. It has the x coordinate is x naught plus delta x, and the y coordinate is in fact f of x naught plus delta x. And similarly, this point has the coordinates x naught is the x coordinate, and the y coordinate is f of x naught. Now if we calculate the slope of this line with the point this and this, then the slope of this line is exactly this quantity. So this line is also known as the secant line. And when we take the limit of this slope of secant line, so when we take the limit that delta x approaches to 0, in other words, we are approaching towards x naught, and as this point approaches to x naught, then this secant line approaches to this tangent line. So we can say that geometrically for the real functions, derivative is the slope of the tangent line. So here is the same situation in a more dynamic way. So we have the secant line, and when we approach this point, in other words, when this h approaches to 0, the distance, then we are getting this tangent line. So this derivative really represents the slope of the tangent line in the real case. Now, our next task is to mimic, to take the same definition of real derivative and take it to the complex case. So here we have a function f. Now this function f is basically a complex valued function of a complex variable. And here the derivative of this function at point z0 is defined in exactly the same way. And as you can notice that I have just replaced the variable x with the variable z in this case. And it's the same definition, f of z minus f of z0 divided by z minus z0, and limit z approaches to z0. So what's the difference? Now here z is basically a complex number, and this z approaches to z0 is really happening in the complex plane. So overall we have the following situation. So this z is really approaching to z0, and of course the first difference that we see from the definition of real case to the definition of complex case is this limit. So when z approaches to z0, so in this case z can approach to z0 from any path. So along any curve we can approach this z0. And another thing which is important is, so when we are approaching z0, then this function must be defined in some neighborhood of z0, because the function is approaching to f of z0 in some neighborhood of z0. So the function must be defined in some neighborhood of z0, otherwise we cannot define the derivative of the function at z0. And on the same lines of the real case, if we just write down delta z to be z minus z0, then from here we can see that z becomes, okay, so from here z is equal to z0 plus delta z. So the definition becomes f of z becomes f of z0 plus delta z, and f of z0 remains the same, and z minus z0 is delta z. So that's why z minus z0 becomes delta z. So this is another way of defining the derivative. And of course when z approaches to z0, then this delta z approaches to 0. Okay, so if z approaches to z0, then this implies the difference between them approaches to 0. So these are equivalent definition, but sometimes it's more useful to use the first definition, and sometimes it's more useful to use the second definition. Now over here, this delta z is basically a complex number, and when we say delta z is approaching to 0, then it means that we are approaching to this z0 along some path. Okay, so this is the interpretation for this second definition, and essentially both interpretations are the same. Now we use this notation for simplification. Of course, the derivative is also denoted as dw by dz, and of course if the function f of z is denoted by w, so w is basically our dependent variable and z is the independent variable, then we denote the derivative in the following way. Or we also use the notation limit delta z approaches to 0, delta w over delta z. Okay, so if our function w is f of z, then in the numerator we have basically the difference in the functional value. In other words, we have delta W. Okay, so in this notation, our derivative becomes, so f prime z naught is equal to limit delta z approaches to 0 delta W over delta z, which is equal to limit delta z approaches to 0. Now this thing in the numerator, this is basically delta W, and now the point is z naught is any point in the domain of the function. So I can replace z naught with z1 or z1 with z2, then of course it's going to be the same definition. So sometimes we drop this subscript of 0 and we just write down f prime of z, which is equal to, so we are just dropping this naught from z naught and we get the following definition. And of course when we say this, then we take this z to be any point from the domain of the function f. Now let's try to solve some example. Let's try to find the derivative of this complex valued function. Now we know the definition. We know that f prime z is basically equal to limit delta z approaches to 0 f of z plus delta z minus f of z divided by delta z. Now in this case f of z is basically z square. So let's use the definition of the function. So if f of z is z square, then f of z plus delta z. So we just replace z plus delta z with z. So in this case it becomes z plus delta z square minus, and of course it is f of z, so this is z square divided by delta z. Now let's open the square and simplify it to find the value of the derivative. If it exists, we will see that first that if the limit exists, then the derivative exists. Z square plus 2z delta z plus delta z square minus z square divided by delta z. Now we can cancel out this z square with z square, and what we are left with is the following expression. So limit delta z approaches to 0 2z. Now we can also take common which is delta z, so 2z plus delta z is common from the numerator, and this delta z. Now since delta z is not 0 but it's some number which is approaching to 0, so that's why we can cancel out this thing. Of course if some number is 0, then we cannot cancel out like this, and then we have the following result. Delta z approaches to 0 2z plus delta z. Now this expression, let's have a look at this expression. Now we are taking the limit delta z approaches to 0, and this expression is basically a polynomial in delta z, and we know that polynomials are continuous functions, and for continuous functions we know that the limiting value is the same as the functional value. So what is the functional value? Just take delta z to be equal to 0 and we have the following answer, 2z. The limit exists and the answer is 2z, so that's why the derivative of this function is 2z. Now the next discussion is, so far in the previous example we saw that we have a function and we calculate the definition of derivative, and at the end we have some answer. Now if there is a function for which the derivative does not exist, now sometimes it's a tricky task to prove that some function does not have a derivative. Now one of the trick that we use to show that the derivative of the function does not exist is the following one. Now we know that the derivative of the complex valued function is given in the following way. Here delta z approaches to 0, but this delta z can approach to 0 in any possible way. So in other words, it can take any path to approach 0. Okay, so in this case, for example, delta z is somewhere over here. Okay, so this is delta z, and then we can translate this delta z to over here, and then we have this value of z plus delta z. So we can approach this point z in any way. So this is one path where we are following a spiral, and then we can take some other path. For example, we can follow this path, or we can follow some other path, for example, moving in a direct way. So moving in a very direct way. So the point is, there are infinitely many ways of taking this delta z approaches to 0. And if we can find two ways, if we can find two paths where the answer to our limit is not the same, then in that case we say that the limit does not exist. So if we can find two curves that end at z0 along which delta w over delta z approaches distinct values, then we say that delta w over delta z does not have a limit as delta z approaches to 0. And in this case, if delta z when delta z approaches to 0, if this value is different for both curves, then the limit does not exist. And if the limit does not exist, then we say that the function has no derivative at that point. So similarly for this definition, so in this definition we have z approaches to z0, f of z minus f of z0 over z minus z0. So in this case, once again, z is approaching to z0 and it can take any path to approach z0. And if we can find two curves, let's say c1 and c2, and if along these two curves we have different value of different limit along these two curves, then we say that the limit in general does not exist. So let's try to solve a very simple example. Now let's apply this trick to show that the function f of z is equal to real part of z is differentiable nowhere. Basically, the derivative at any point of the complex plane does not exist for this function. Now what is this function? So the function is very simple. If we take z is equal to x plus iota y, then this function means the real part of x plus iota y, and this is equal to x. So it's a very simple function. Now if we want to use the same trick and we want to find two paths along which the value of the limit is not the same, then we have to choose two paths in this case. So the first path that we choose is basically a curve which is parallel to x-axis. So we are approaching z0. So let's say this is the point z0, which is equal to x0 plus iota y0. We are approaching this point along a line parallel to x-axis. So in other words, we take this line and we are approaching this line. So we can approach from left side or from right side, but we are approaching the point z0 along this line. Now along this line, we can see that the value of y is basically fixed, and it is fixed to be y0. So on this line, our z is equal to x0 plus. Okay, so the variable x varies, okay, but the value of the y is basically fixed, and it is equal to y0. So when we say that we are approaching z0 along this curve, then we take z to be equal to x plus iota y0. So in this case, the derivative becomes the following. So f of z is the real part. Now in this case, as we know that z is equal to x plus iota y becomes x plus iota y0, and then this approaches to x0 plus iota y0, and the real part, okay, so of x plus iota y0. So once again, z is basically replaced with x plus iota y0 instead of x plus iota y. So minus real part of x0 plus iota y0 divided by x plus iota y0 minus x0 plus iota y0. Now cancelling out and simplifying, we have the following situation. Now the real part of this thing is basically x, and the real part of this is x0. So in the numerator we have x minus x0. In the denominator, so these will cancel out and we have x minus x0. And so when we cancel out this thing, then we have the limit to be equal to 1. Now on the other hand, if we take another path, so now we are approaching z0, which is equal to x0 plus iota y0 along the curve which is parallel to y-axis. So in other words, now we are approaching this point along this line, and of course this point has the coordinates x naught. So in this case, the variable z is basically x naught, so because x naught is fixed, and y is the free variable, and the only thing which will be changed in x plus iota y is this y, and x naught will be fixed. And in this case, once again, we will follow the same steps, and we have the following scenario. Now we can see that in the numerator it has real part of x naught plus iota y, because now z is equal to x naught plus iota y. So we have x naught, and the real part of x naught plus iota y naught is once again x naught. So, and in the denominator we can see that x naught will cancel out with x naught, and we have iota y minus iota y naught. Now in the numerator we can see that it is x naught minus x naught, which is 0. And the denominator is not really 0, because y is approaching to y naught, and y is not equal to y naught. So this is some non-zero number, so the value of the limit is equal to 0. So we can say that this function, which is the real part of z, is differentiable nowhere. So in this discussion, we have defined what is the derivative of a complex valued function. We solved some simple examples. This was the first part of our discussion on the derivatives. In the next discussion, we will explore further about the properties of the derivatives and some further examples.